All right, it's hard to believe. Week 4 of online Chem 104. This is Lesson 1, EPR spectroscopy. Let me start by saying that the goal of this unit of this week is not to teach you how the instrument works, but it's to show you some data and give you the basics of interpretation. If you want to learn how instruments work, you should take Chem 112, and maybe one day Chem 112 and Chem 104 will be perfectly synergistic, and Prof. Hawkins will teach you how to acquire the data, and I will teach you how to interpret it. But for now, we have a little bit of overlap, and I like to add in a few of the instruments that are especially useful in inorganic chemistry. NMR is a type of spectroscopy you should be familiar with, and it involves radio frequency radiation that causes a population inversion of nuclear spin and a strong magnetic field. EPR spectroscopy is pretty similar. Microwave radiation, which is lower energy and lower frequency, causes a population inversion of electronic spin inside of a weaker magnetic field than seen in NMR. The energy difference between the spin-aligned case and the spin-anti-aligned case is given by this equation, which incorporates G sub E, the proportionality constant G for the electron, mu sub B, the Bohr magneton, and B naught, the magnitude of the applied magnetic field. The Bohr magneton relates electronic spin to magnetic moment, and we saw that in the magnetism unit, and it serves a similar role here. For a free electron, the magnitude of G is almost exactly equal to 2. We derived this in the magnetism unit. But much like chemical shift, this value for G is highly dependent on the chemical environment of the electron. The G factor is the EPR equivalent to chemical shift, the delta in NMR. Organic radicals typically give G values that are close to 2. But transition metal complexes can have spin-orbit coupling, which is quantum mechanical coupling of the electron spin to orbital angular momentum, or local magnetic fields due to metals or other unpaired electrons, to give very different values of G than 2. The magnetic moment of an unpaired electron can also have directionality, and this can tell us a lot about the symmetry and shape of the orbital that the unpaired electron is in. And what these G values are the projections of the G vector along X, Y, and Z. So for the isotropic case, we would have a spherically symmetric electron environment, and the Gx, Gy, and Gz would all be equivalent. There are 3 different anisotropic cases, however. The first is an axial spectrum where the G that is parallel to the applied field is less than the G that is perpendicular to the applied field. The second axial case is where there would be the G values that are parallel to the magnetic field are larger than the G value that is perpendicular to the applied field. And the third case is if all 3 values were different. And so in this rhombohedron, I have the Z and X and Y directions are all different in magnitude. I'm not expecting you to remember the details of these different axial and rhombic cases, but just recognize that different environments of the electron can lead to different shaped spectra, and I'll show some examples of these spectra on later slides. In addition to the G value, which is equivalent to chemical shift, you can also have additional coupling features. For example, a hyperfine interaction is when you have the unpaired electron that interacts with the atom on which it resides. There's an example in the text that shows the electron coupled to a copper center, which gives a 4-line pattern since copper is a spin 3/2 nucleus. The multiplicity of the line is 2n plus 1, so with a 3/2 nucleus, times 2 gives 3, add 1 gives 4. A super hyperfine interaction is one where an electron interacts with another atom, not the atom on which it resides. It has a very similar type of coupling pattern with a 2n plus 1 splitting rule. For example, if you label a nitrogen as N15 instead of the naturally occurring N14. That's a spin 1/2 nucleus, and if you had a copper nitrogen bond, the electron might see the 4-line pattern due to the copper with an additional 2-line pattern due to the nitrogen. This A coupling is equivalent to the NMR J coupling that you've seen in NMR, and it's often reported in centimeters, reciprocal centimeters or wave numbers, but you will often see it reported in Gauss instead of wave numbers. The rest of the slides are some example data from my PhD work, and before I show that, I want to give you some final information about data presentation. First of all, EPR signals are usually extremely broad. Like we discussed in Chem 110 lab, when you're doing paramagnetic NMR, you often see very broad line shapes due to observation of all of the possible environments of the NMR nucleus instead of the average signal. That's due to the rapid relaxation of the unpaired electron that the unpaired electron provides to the nucleus. It's a similar idea in EPR where we see more rapid relaxation and therefore broader signals. So instead of plotting an absorption spectrum, almost all EPR spectra are presented as derivative spectra. So the next spectra that you're going to see are all derivative spectra, and I'll explain what each spectrum is showing us. The first part of my PhD work was exploring low coordinate and low valent titanium compounds. So this is a titanium 3 bis amide halide complex with a coordinated lithium chloride, and the lithium is further coordinated by this bidentate TMEDA ligand. This is one of the most air-sensitive compounds I've ever characterized. It was a mossy olive green floss or like fluffy cotton that just reacted immediately in air to turn brown and sort of melt and decompose. The mu effective I calculated for this was 2.22 Bohr magnetons, which is what you would expect for one unpaired electron on the titanium center. And this is a rhombic EPR spectrum. We can see 3 different G values here, here, and here. And so the peaks in the derivative spectrum are where the G values are. You can see they're 1.980, 1.964, 1.930. So they're not very different from 2 in this example, but we see that X, Y, and Z coming out of the plane are all different in this environment, and so the unpaired electron on titanium sees a rhombic spectrum. The overall goal of that project in graduate school was the synthesis and characterization of a titanium 3 alkyl. So here's a titanium with 2 amide ligands and a single carbon bound to it. So it's a approximately 3-coordinate titanium center. There is some interaction with the arene of this aromatic ring to the titanium. So how would you classify this ligand if you were thinking about it as an organometallic? You've got a nitrogen, which is an X ligand, and this is behaving like an L. This nitrogen is behaving as an X and an L, donating X in a sigma fashion, and then the pi orbital on nitrogen, pi donor. And carbon is only an X ligand. We'll talk more about X-ray crystallography in a later lecture this week. And I can still see this crystal almost 25 years, more than 25 years later. It was a beautiful emerald green, amorphous crystal, just a beautiful color, and this was the crystal structure we obtained. The EPR spectrum is, again, very similar to the one we saw for the titanium 3-8 complex that on the previous slide, with 3 G values corresponding to X, Y, and Z. And again, we have a rhombic symmetry because there's no axis of symmetry in this molecule. This next compound is representative of a series of compounds I made, so molybdenum, E, and RAR3. So it's the same ligand that was on the titanium center, and E was either oxygen, sulfur, selenium, or tellurium. And I made and characterized all 4 of those compounds plus additional for that part of my PhD work. And in this spectrum, which is of the tellurium derivative, which has this spectrum, we can see, again, 3 G values. They're very widely separated. The G values are 2.1, 1.9, and 1.8, so a little bit more spread out than in the titanium case. But the interesting thing that you can see in this spectrum is the hyperfine coupling to the molybdenum center. Some of the lines are buried, but there is a 6-line pattern due to coupling to the spin 5/2 nucleus of molybdenum. So I'm trying to illustrate some of these features. They were hard to visualize, and we had to do some modeling in order to get the correct A coupling values that I report on the screen. To give you a sense of how far computational chemistry has come in the last 20 to 23 years, in this upper right corner is the X-ray structure. We didn't even attempt to model this full structure using DFT, although I would now. I would have no problem modeling this using modern computation. We published this version with our DFT collaborators at that time, where we modeled the bulky alkyl aryl amide as an NH2, and it gave actually the correct structure, or a reasonable approximation of the correct structure, where we had 2 of the amides were vertical and 1 was horizontal. It turns out in the X-ray, 2 were more horizontal and 1 was vertical, and that has to do with the subtle interplay of steric factors. These ligands just didn't fit very well. This last example is an example of an axial spectrum. This is not work from my PhD advisor, although it is from my PhD advisor's PhD advisor, my academic grandfather, Dick Schrock at MIT, who won the Nobel Prize for early metal carbene chemistry, also has done a lot of work with molybdenum N3N compounds like this, so very similar to the compounds that I worked with on my PhD. This molecule has a 3-fold axis of symmetry, and it changes the EPR spectrum to where we have now 2 lines, the parallel and perpendicular lines. And this paper goes into a lot of detail about the solvent effects, and you can basically ignore that. But what we can see is an axial spectrum with a G parallel and a G perpendicular. The perpendicular G value here is 1.61, and this G value is 3.03. So the take-home message here is we're just scratching the surface. I want to explain EPR and let you know it exists as a technique, that you can begin to learn some things about the electronic structure of the electron, the geometry of the electron, and the local environment of that electron. But if you wanted to dive deeper, you could. Whole books have been written about EPR data analysis. So if you're interested, we can talk more about it in office hours or next year. This is the end of the EPR module. We will be moving on to another technique in Lecture 2.